And we'll start from the current slide. Now, sorry about my throat. This has been a cold that looked like it was going away and came back, and looked like it was going away and came back. It seems to be on the mend, but it still doesn't sound very good, so sorry about that. Only announcements I know about, I think I've announced this one before. If any of you, this came from someone at UAB, a postdoc in their merit program, whatever that is. She's a microbiologist, I believe. And something crossed her desk about a biopharma manufacturing. That if any student's interested in biopharma manufacturing, I take that to mean making drugs. If they're interested, they can participate in a 1-week summer program this coming summer, 1 week, and they will pay you $1,000 to attend and pay your transportation there and back. So it sounds like quite a good deal to me, okay? And they must be pretty serious about recruiting students. So anyway, all she said in the email was the deadline is January. Not when in January, not think. Now, there was a link on her email that you could go to for a website. You can find out, I'm sure, all the information you needed, including the deadline and stuff like that. But one of the other students in my class borrowed it to get the information and never returned it. So I don't have it anymore. I can look it up and get it. Yeah.
It was a random email?
I'm sorry?
It was a random email?
A random?
Email?
No, it came from Dr. Wilson here because this woman had sent it to her. And she said it was
Legit.
it seemed like it was legit. Yeah. And no, it's somebody that Dr. Wilson had a relationship with, and she said, in case any of your students are interested, here's a really good sounding opportunity. So there's that. And then the other thing is we have been undergoing this week, yesterday and today, our SACS visit. I don't know if y'all are familiar with that. Southern Association of Colleges and Schools. They're the accrediting agency for the whole southern tier of states, at least the southeastern, I think most of the southern states. We have been in the process for this. It happens once every 10 years, whether you need it or not. They reaccredit the schools. And we have been involved with getting ready for this for well over a year. And people have been working very hard and doing a great job getting things together. Most of it's been done paper-wise, actually not paper, electronically, back and forth between them. And so they had questions, they had places they thought we needed to improve. We did that. And then ultimately they decided, yeah, it looks good. We're going to come visit and see if you're actually doing what you say you're doing. So they've been here this week, and as far as I know, it's been going quite well. So hopefully they have left, or if they haven't left already, they'll leave tomorrow sometime, and hopefully it'll be in a very pleasant departure, you know, that everybody's happy with everything. I'm pretty sure that will be the case, but in case it's not, it's going to be easy enough to, I guess, get any of their complaints or recommendations corrected, and that'll go back to them. But the tough part's over with, okay? Actually, that was already over with, but the visit is always, can be stressful, and I think it went over very nicely. So if you do see a bunch of people walking around on campus, very official looking, that's probably what they are. They could be here tomorrow as well. I'm hoping they found everything so well done they left early, but we'll see. All right, any questions on anything we've covered so far? Okay, just a quick rehash of where we are, where we've been, and where we're going. Everyone did turn in the first test, and I think I've returned them all to you. All but one person has turned in the second test. Okay, so as soon as you can get that in, that would be great. and there are 2 people that haven't turned in the 3rd test. The 4th test, I've only received, I think now 4. I got 1 today. So I've gotten 4 of those in. What's that? You don't have the 4th test. Okay, I thought maybe not, so I was getting things lined up here. Okay. Everybody else got the 4th test, right? There, 2 of you have turned it in already. Here, let me point out a couple things to you. All right. Number 8, they gave all the information you needed except what was the frequency of the whistle. So I had to back calculate and get that it was 585 hertz. Okay? So I wrote that in. They gave the frequency, the velocity of sound in air. Number 9, they didn't tell you what the velocity of sound in air was, so use the same one, 1090. And they also went as far as saying the car horn produces a sound at a frequency of, and then didn't put it in. I calculated and it came out 5,000 hertz. So that is it. So those are the 3 things to add or note on that. All right. Now, we are in chapter 17, and 17 is basic electricity, and we are only doing selected sections of 17, and we finished most of those. We did section 17.3, 4, 5, 6, and 7. No, 6, 7, and 8. We are now in section 17.9. That's what we'll be starting tonight. Hopefully we'll finish this tonight and move on to magnetism, which is chapter 18. Now we're only covering 3 sections in 18 and then 2 more sections in 19. So we're going to combine those for the last test. That will be your last test, technically your final exam just because it's the last test. And that I hope to get to you by next, not this coming Thursday, the Thursday after that, because that's the Wednesday after that. That's the last time we'll meet. That's the Wednesday after Thanksgiving. And that's the last time we'll meet before the final. So the final exam is due in the following Wednesday. Well, okay. So the last time we'll have class is that Wednesday after Thanksgiving. Then the following Wednesday is when you come to turn in your test. Now, you can bring it any other time, but I'll be here that Wednesday night to pick up your test. Now, if y'all want to have pizza or something, we could do that too, but that's up to you. Okay. We'll talk about that as we get closer. All right. Let me get the new arrivals. Okay. Is it Kayla? No. Tierra. I'm sorry. I knew that. Just can't find you. There you are. I was 1 line off. Okay. And Emily? Yeah. All right. 1, 2, 3, 4, 5, 6. 3, 6. Got it. All right. Any questions before we get started tonight? Yes?
I know it's gonna sound odd. Can I get another test? I hate, you know how people, like kids used to say they thought they did homework. I don't know what happened to my test, and I don't think you'll be able to read it. So can I?
I can read that. You've seen my writing. It's way worse than that.
I'm saying, like, with it being all balled up and such.
That's fine.
Okay, let me go change something.
Okay. That'd be fine. Okay. So, tonight we're starting in 17.9, and hopefully we'll finish it. It's not a short section, but it's relatively short. We should finish it tonight, and that's all we're going to do in Chapter 17. So I'll give you your Chapter 17 test tonight, and then we'll start Chapters 18 also tonight. And then next Wednesday we have class. We'll continue with 18 get as far as we can, maybe into 19. Then there's Thanksgiving week, and y'all have the whole week off. We only have Thursday and Friday off, but y'all have the whole week off. So there's no class that Wednesday of Thanksgiving, Wednesday before Thanksgiving. And then we'll have one more class the Wednesday after Thanksgiving. That'll be our last class. I'll give you your final exam at that point, and then you return it sometime by the next Wednesday. I'll be here that Wednesday night, so you can turn it in here. But if you want to take it by the Bessemer campus or the Birmingham West campus over there on a Friday, anytime I'll be able to take it. So during my office hours. And even if not on the Bessemer campus, you can slide it under my door if I'm in class or something like that. Okay. And it's Jihan, right? Jihan? Is it Jihan? Robert. Okay, got it. Sorry about that. Okay. Okay. Any questions before we get started tonight then? All right. Up till now, we've talked with electricity about circuits. Okay, what's required in a circuit, you have to have a potential difference. That's I've got my recorder going. Okay, potential difference is your voltage source, your energy source, whatever you want to call it there. Often called E for energy source, also for EMF, which means electromotive force, which is not a very good term because they just use E, or V, voltage source. So when you see this in your diagrams, that's the voltage source. That's where the charges get their energy, okay? Then you have to have wires to connect things. That's the pathway, okay? Then you have to have a load, something that's going to use that energy. That's often called a resistance, but it can be other things, and we'll talk about some of those other things in the next chapters or two. All right, and so we talked about circuits, charges, flow of charge is current, which is amperes, which is coulombs per second. Coulomb is the charge. Voltage is, okay, when we got to Ohm's law, which was a few sections ago, voltage is equal to current times resistance. That's amps times ohms yields volts. Now, volts is one of those strange things. Capital V stands for voltage, the parameter, but it also is the unit volt. Capital V there too. One of the few times that you'll use the same symbol as the parameter as it is the unit. And then we started looking at different types of circuits. You have series circuit where the current goes through every element, okay? In a series circuit, the voltages add, the current is constant, and the resistance is add as you go around. In a parallel circuit, which has multiple pathways, the voltage comes up and the current splits, and some goes here, some goes there, some goes there, however many pathways you have, then the current splits, whereas in a series circuit, current is constant. In a parallel circuit, the current splits, the voltage is the same across everything, and the resistors add according to their reciprocals, which is really a strange way of adding, but it is what they do. And what's even stranger, the more resistors you put in a parallel circuit, the lower the overall resistance is. Whereas the more resistors you put in a series circuit, the greater the resistance is. The more you put in a parallel circuit, the lower the resistance gets. Really a strange concept, but it does work that way. So what we're talking about this evening is starting with what they call a compound circuit. Let me get my pen set up. Okay, a compound, my writing stinks, circuit, compound circuit contains a combination of resistors Okay, a combination of resistors in series. For those who just came in, I apologize for my cough and my voice, but it's on its way out, I think, but it's fighting every inch of the way. And in parallel. My pen is awfully slow here. What's going on? Sorry. I may have to stop and get some more water. Okay. Is it Jihan? Yeah, okay. Okay. All right. We're just beginning 17.9. If you got your text, it's on page 478. Okay. In parallel resistors in series and in parallel arrangements. Let me put that last word in here. Okay. Okay. Sorry. Now, here is one example of a circuit, and this is how the book approaches it, which is okay. I don't usually quite break it down this much detail, but it is a good way to look at it. This is a compound circuit. These two resistors are in series with each other, but they're in parallel with the third resistor here. So, our rules, how do we handle that? Well, they're not telling us anything about the voltage across here, except we know the same voltage is across these two. Now that's weird. I wasn't anywhere close to this thing. So nothing I did caused that. All right. Who has the bad vibes, huh?
It's the weather.
Okay. It's Saks. It's their fault. Okay. I don't know what. Ah, there we go. Let's not touch another thing. All right. Whatever the voltage is across these two, it's the same as the voltage across this one. You have one voltage drop here, another voltage drop here. Now, whatever current is coming in here, part of it goes this way and part of it goes this way. So the current splits, okay? The same current goes through these two, but a different current goes through that. So, how do we analyze the circuit? Well, since these two are in series, we know that resistors in series add their resistances. So we can add R1 to R2, and it acts like one big resistor, which we'll call R4. Okay? Now you've got R3 and this big resistor R4, they're in parallel. Well, what's that equivalent resistance? Okay, now that was the weird one, as if there aren't enough things weird. For those who weren't here before, let me review how you add resistors in parallel. This will be the result. One is R5, so 1 over R5 is equal to 1 over R4 plus 1 over R3. Really strange the way those resistors add. Now, we'll be working some examples later, so we'll go over the easiest technique for doing this, depending on what kind of calculator or your phone or whatever you're using for that. There are some easy shortcuts to do these calculations without having to mess around with fractions, which I know you love your fractions, but you won't have to mess with the least common denominators. All right, so example 1, this is the figure for it. And circuit B, they say here, is equivalent to circuit A if you add the two resistors 1 and 2 to make resistor 4. Circuit C is then equivalent to circuit B and equivalent to circuit A if with circuit B you add the resistors according to what I just did there in parallel. Okay? And that's all there is to do. We just did example 1. They worded it here, we did the same thing. The only thing I didn't do, I said it but didn't do it, so I'll write it. R1 plus R2 is equal to R4. And once you got R4, then you get R5 by 1 over R5 is 1 over R4 plus 1 over R3. Okay. Now, example 2, top of page 479, is a different setup. So let's take a look at it. I don't think we have a slide. Oh, yes, we do. There it is. This is a different setup. Here we have resistor 1 here that's in series with this compound with this parallel set of resistors there. So how would we analyze this one? Well, we have to deal with the combination first. So we say, does anyone remember how you find out the equivalent resistance of this one? In other words, what's your R4 here? These are in parallel. Hint, hint. How do you get R4? 1 over R4 is equal to 1 over R2 plus 1 over R3. So once you get R4, then you have it here. Now R1 and R4 are in what relationship? Not parallel, but series. Series. Now, how do you get R5 then, once you've got R4 and you already had R1? What's the relationship there? What do you do with series resistors? Add them. R1 plus R4 that you calculated here is the new R5. And that's how you go. Okay? Any questions on that? Okay? So that was example 2. Now we do some actual circuits. That's just how we do the resistor part. So we'll now do it with an actual circuit. That's the summary. Okay? So we'll back up here, go to my backup slide, and go from current slide. Okay, have to set my pen back up. Okay, here's example 3. Find the total current in the circuit shown in 1753. Okay? Here's what we know. Now again, sometimes they use E, sometimes they use V. They're using E now. It's equal to 115 volts. Now I told some of you who were here before earlier that if you see 115 volts, you know it's not a battery. This thing sort of represents a battery. This is not a battery. This would be a plug in the wall. The wall alternating current typically is around 115 volts, 120 volts, somewhere around in there. You seldom will run into a 115 volt battery. That is a powerful battery. So I doubt if that's going to happen. Okay? Now, wow. This is just like, oh, they've got the drawings backward. Okay. Figure 1753 is over on the right-hand margin, and then they show the others first. Okay. So let's get this. Here we come to a node, and in the node we have one branch going up and one branch going down. In the upper branch you have two resistors in series with each other, and in the lower branch you have one resistor in parallel with the other two, and then from here it comes back to the battery. Okay? And what they're looking for, the total current in the circuit. Now, most of the time our convention is to put the current going from positive pole to negative pole, even though we know in our heart of hearts that the charge is moving the other direction. Is it coming? There it is. Okay? But it doesn't really matter. It's really not the current that's doing the work, it's the field. So the field is always in the direction from positive to negative. So that's what's important. So don't worry about this. Here they tell us that R1 is 10.0 ohms. That's the unit for resistance. R2 is 32 ohms. And that should have a 0.0 after it too, sorry. Okay, get back there. Okay, and R3 down here is 19.0 ohms. Okay, there's our setup. It says find the total current in the circuit shown. Yes? Oh, man. Okay, sorry. Let me know. All right. Where would you begin? To get the current, what you have to have is what we call the effective resistance of all those resistors. So where would you begin to get the effective resistance? You let me know. So again, R1 and R1 and R2, what do we do with them? We add them together because those are in series. And what does that give us? Let's just call that R4, because that's what the book calls it. And what is that? A little louder, I can't hear. 10.0 plus 32.0. Pretty easy math. 42 ohms. Okay. So now we've got R4. We could write that as one resistor, but this is what it would be equivalent to. Okay? Now, what does that give us? R4 up here, R3 down there. Those two would be in parallel. How do we determine the effective resistance of two parallel resistors? Or 3 or 4, however many. What's that formula? And we're going to pretend this is a new resistor here. Let's just name it R5. How would we determine what R5 is? Okay, add R3 and R4. How do you add them? Not like we did R1 and R2. Those are in series. You add their reciprocals. So 1 over R5, that's what we're going to call the effective resistance of the whole shebang there, will be 1 over R4 plus 1 over R3. So let's plug and chug. 1 over R5 is equal to, now, I'll write it in, 1 over 42. I didn't put my 0.0, shame on me. 0.0 ohms plus 1 over 19.0 ohms. Before we do this, someone make a guess. What would you estimate R5 to be? Make a guess. You think it's smaller than R3, in between R3 and R4, larger than R4? What would your guess be? You're calculating. What would it be? Anybody? Just make a guess. 3 choices. Less than R3, between R3 and R4, or greater than R4? Okay, let's see. Now, do you know how to do this kind of math? I'll tell you the easy way if your calculator will do this. Now, you have to find a key on your calculator that's either 1 over x or x to the minus 1, or something like that. Can everyone find that key? Got it? If you can't, ask me and I'll see if I can find it for you. I'm kind of used to looking at calculators and phones and stuff like that. Has everyone found the key? Okay. Here's the easy way to do this calculation. You press 42. You don't have to do the 0.0, but you can if you want to. Then press the key. I'm just going to call it the key. Okay, press that key. Then you do plus, and you do 19, and press the key. And then you do equal, and then press the key again. And that should give you a result. You might have to do another equal. I don't think so. What do you get? 13.08. 13.1, I'll call it, ohms. Okay? So what did it turn out being? Less than either of the other two. That will always be true about resistors in parallel. The effective resistance, the total resistance of those resistors will be less than any one of those in parallel. Okay, does anyone need for me to do that again? Go through it again. Have you? I'll be glad to look on and watch you do it. Anyone need to help? Okay. Did everybody get 13.1 ohms? So your R5, which incorporates all of this is going to be your R5 then. Now you know your resistance of the system. You know the voltage in the system. How do we get the current? Any ideas? Somebody's law. We referred to it many times. Ohm's law. How does Ohm's law go? It has one of 3 forms. Pick any one of the forms. I is equal to, what do you say? E over R. Perfect form for this problem. Because we know the E, that's 115 volts, and we know the effective total resistance, that's your R5, which we come up being 13.1 ohms. So if you divide 115 volts by 13.1 ohms, what do you get? About 0.8 or 0.9? 8.78. Say again? 8.78. 8.78 what units? Amps. Very good. 8.78 amps. Okay? Let's see how the book did. That's over on the next page. Oh, there it is, 8.78 amps. Okay? What are the other two renditions of Ohm's law? You gave me one of them, I is equal to E over R. What's another one? This pen is doing strange things today. The whole system's being strange tonight. What's another way to express Ohm's law? Oh, we already did I. What's another one? We did I equal E over R. What's another one? Say again? That's perfect. R is equal to, not I over E, E over I. You see, the E's always on top, okay? Except when it's out front. And then how do you do E? And sometimes it would be V, either E or V, whichever you want to use. What would it be? Not over, I times R. Goodness, this pen is doing weird things. Okay. I times R. So those are the three forms of Ohm's law. If you're looking for current, it's E over R. Looking for resistance is E over I. Looking for voltage is I times R. Current times resistance. Okay? Do y'all like to use the triangles or circles or not? It's up to you. You can use them if you want to. Doesn't matter. All right, we got example 3 done. Any questions on that? All right. Now, before I go to the next one, got a question for you. How do you eat a 5,000-pound elephant? One bite at a time. Very good. So even when you see these things that look really hairy and messy and terrible, don't fret it. Take it one step at a time. So here we have one. Yeah, okay, she's already been here. Okay, here's your voltage. This is not a battery, even though that's a symbol for battery. This, your E is equal to 120 volts. What's that bar over the 0 mean? It's a significant digit. You're absolutely right. Okay. It comes up from here, comes over to here, and then splits 3 different ways. Okay? Up here you're going to have R1. That happens to be 7.00 ohms. Here we have R2, and R2 is 35.0 ohms. And then you have R3 down here, which is 25 ohms. Okay, then those 3 come back together in the circuit and proceed. But here they get down here and split again. They have R4 down here. Being 20.0 ohms. And then they have R5 down here, which is 62.0 ohms. Okay. Then finally it leaves here and goes back to the battery. All right. There's your circuit. How would you begin? Well, you get your thing back on. This makes no sense. Okay. tell me where you would start on this problem. Just point me where you want to start. We'll go from there. Okay, how would you add those? What kind of circuit are they on? What kind of circuit is that? Those three? Somebody help. What's that? One more time. Okay, my hearing is terrible. Did I say what? Okay. One more time. Okay, I'm still not catching it.
What's it called?
Oh, you want me to answer? Okay. These three are parallel with each other. Look at that. They're parallel. This is a parallel circuit. So how do you add resistors on a parallel circuit? And that may have been the word you were saying.
I think so.
What were you saying? Reciprocal. Okay, I got it. I thought it sounded close to something. Yes, you add them by the reciprocals. So what you want to call that one when we combine to get an equivalent circuit? Come up with a new name for it. R sub. You've used 1, 2, 3, 4, and 5. Okay, let's use 6. So 1 over R sub 6 is equal to 1 over R sub 1 plus 1 over R sub 2 plus 1 over R sub 3. So plugging in 1 over R6 will equal 1 over 7. You don't have to put the 0, 0 if you don't want to. Plus 1 over 35 plus 1 over 25. Now you remember how to do that on your calculator? But you're absolutely right. You add them reciprocally. I just couldn't understand what you're saying. Okay? Remember the process? The key you look for is either 1 over x or x to the minus 1. Some calculators use 1, some use another. It could be y's, it could be a's, it could be whatever, something like that. Everybody found the key? So what you would do is do 7 and that key, whatever that key is, plus 35, that key, that reciprocates it, plus 25 times that key, not times, but hit that key. And then you do an equal sign, and then whatever answer you get, reciprocate it. And what do you get? Okay, so your R6 is 4 point what? 72 ohms. Okay. What's your good check on that? It better be less than any one of the resistors in there. And because one of these is a 7, it's got to be less than 7. Certainly going to be less than 35 and 25. So that's R6 is going, or this trio here, this group of 3 resistors in parallel is acting like a single resistor with that resistance. Okay? Seems bizarre. What do we do next?
The book has 4.73. The answer was 4.729.
Okay, that rounds it up to 3. Okay, I thought you had already rounded. Okay? Yeah, the 9 bumps it up to 3. All right. What's the next step? Help me.
You gotta add R4 and R5.
How do you add those? Same answer. Second? Okay. By reciprocals. 1 over R7, we'll just name it that, is equal to 1 over R4 plus 1 over R5. And that would be 1 over 20 ohms plus 1 over 62 ohms. Just someone hazard a guess about what answer you think we might get. Something less than 20, between 20 and 62, or greater than 62? Less than 20. And this is going to give us 1 over R7. So how do you do that on your calculator? Help me, somebody. Anybody? Tell me how you punch it in or press it in. 20 reciprocal plus
62
reciprocal equal,
reciprocal.
and what do you get? A little louder. 15.1. What unit? Ohms. Ohm. Okay. 15.1 ohms. Okay, now you've got one resistor here that looks like this one, and that takes the place of those three. And then down here, you've got one resistor that looks like this one, taking the place of those two. How are those? Now, what I think I'll do, if you don't mind, is erase everything but R7 and R6. Is that okay? Because I don't have room to do it. So I'm going to erase all this. I could have left part of that. I wish I'd have thought of that sooner. And erase this. Okay. Now, what we have now is a circuit that looks like this. And this is your R6, which we calculated to be 4.73 ohms. And down here, this one we placed the other two, and this is your R7, and that was approximately 15.1 ohms. So, what do we do with that circuit? You just add them because these are in series. The same current goes through every element now that you got rid of the parallels. Let me make sure I know what they're asking for. Find the equivalent resistance. That's all they're saying. So the equivalent resistance, we'll call it R sub E. Sometimes they'll say R total, whatever. What would that be? Not that hard. Help me, help me. Say again? 19.8. The 3 goes away. 19.8 ohms. That's the equivalent resistance of that original circuit. Now, the interesting thing is that's less than all but one of the original resistors. That R1, which was 7. The effective resistance here is 19.8, which is less than 35, less than 25, less than 20, less than 62. The equivalent resistance is less, but it can be more now because you add resistors in series, which was what we did. All right. So they call it R8. No, I'm sorry. Yeah, they called it R8. I called it RE, and they get 4 point, wait. Goodness, okay, there we finally see it. 19.8 ohms. Very good. Now, before we leave that slide and the picture, example 5 says, find the total current in this example. So how would you find the current? Current traditionally is in the direction from high potential to low potential. So this is the current. How would you find the current? Okay, divide what? I is equal to E over R. Excellent. The R we use is the effective resistance, or the total resistance. So this would be 120 volts divided by 19.8 ohms. Anyone get what that is? 6.06. What units? Amps. Very good. Oh, look at that. They got it right too. Any questions on that? Is this making sense? All right. Now we go to back to our books, PowerPoint, and back to the next slide. Here is a summary now, characteristics of series and parallel circuits. Okay? Just a reminder, we've done them each individually, now we're putting them together. In a series circuit, all the current goes through every element. So the I is equal to I1, equal to I2, equal to I3. Every current is the same all the way around. The resistors add just like you would expect them to, R1 plus R2 plus R3, whatever, if they're in series. And your voltage, this is your voltage source. The voltage drop across each resistor would be V1, V2, V3, V4, and you add those together and you come up with the same resistance voltage you had at the beginning, the battery. But in a parallel circuit, the currents add because the current splits. Every time you have a parallel circuit, the current has a split and goes various places. So your I is equal to I1 plus I2 plus I3, however many you have in parallel. Your resistors add by reciprocals. 1 over R is equal to 1 over R1 plus 1 over R2 plus 1 over R3, as many as you have in series, in parallel. But your voltage, as long as all you have is one parallel circuit in there, the voltage is the same across every resistor, because the voltage across here is here, is here, is here, all on those parallel circuits. So there's your summary slide for these. Now, let me give you an example. Does anyone remember the old Christmas lights? That if one of them went out, they all went out. What a pain in the neck they were too, weren't they? Those were in series because the same current went through every one. If one filament went, the whole circuit was dead because all the current went through. And if one filament broke, then no. Okay, most of the more modern Christmas lights, if you'll notice, they have looping wires between them. You don't have just one wire going, you have a series of wires, 2 or 3 between each one, and they loop around making a parallel circuit. Okay, now, we have some outdoor plants that we like to keep from year to year. Our garage is big enough to keep a few of them, but not all of them. So what we do, we put up a little greenhouse behind the garage, and not very big, but it's big enough to hold what we got. And we put the plants in there in the wintertime. But when it gets as cold as it did last night, okay, we got to do something else. So what we did, my wife read about this somewhere, and it sounded like a good idea. Now, not the old Christmas lights that we were talking about, but the old parallel lights that were hot. You know, the bulbs got really hot, and if you kept them on too long, you might burn up your tree. People are getting away from that. They're using LED lights and things like that now that are cooler. But we had, Karen found somewhere, someone suggested if your plants need warming, get old Christmas lights because they give off a lot of heat. So that's what we used. We went to my brothers and sisters and sister and everyone we knew and said, do you have any of the old lights that get so hot you don't use them anymore? Oh yeah, we got to throw that. We meant to throw them away. But we have them. So we got several strings of those lights and put all over in my greenhouse. Okay? It's a little greenhouse. So I put way more lights than I needed. In fact, I only had a plug that had 3 receptacles on it. So I could put one in each. But then what I said, well, let me plug 2 strings together. And that did okay most of the time. But then I said, well, I've got more. Let me put 3 strings. As soon as I did that, the fuse went. Because all of those lights were in parallel. And the more I put on, the less the resistance was, the more the current was, blew the fuse. So I was restricted to no more than 2 lines per plug. And that's enough, okay? And what it also gives me is a very pretty greenhouse because it's all lit up like a Christmas tree, you know, with multicolored lights. So just a Christmas example of parallel and series circuits. All right. That's the last slide in the slide set. It's not the last section in the chapter, but it's the last one we're going to cover. But your problem set 17.9, I would do any of the odds 1 through 5. That's using one figure. Do any of the odds 7 through 11. That's the second figure. Then do any of the odds 13 through 19. That's the third figure. And then do any of the odds 21 to 25. That's the fourth figure. Okay? So do some of each of those to make sure you understand. Now, before we leave, there's a electrical and electronics engineer, physics on the job. Interesting reading, but I doubt if any of you are planning to go that route. And then 1710 is about electrical instruments, which act like resistors and stuff, but we're not going to go over that. There are voltmeters, ammeters, and ohm meters. Voltmeters measure potential difference or voltage. Ammeters measure current or amperes, and ohm meters measure resistance or ohms. But you don't need to do that. Then there was also voltage sources, 1711. You can have batteries. You can have a variety of types of batteries, lead storage batteries, dry cell batteries. And then 1712 puts the batteries in series or parallel. The same principle holds, but some of the calculations are different, but we'll assume you don't need to know those. So we're not going to go over that. 1713 is talking about electrical power, and I'm trying to think if you're going to need this in the future. Just in case you do need it, I'll give you the formula. Don't sweat it, but this is the formula. And it's a good review anyway. Anyone remember what a volt is? Hopefully I've said it enough times you recall. A volt, or potential difference, is energy per unit charge. Capital E is energy, V is volts, and Q is charge. Okay? And this is 1 volt is 1 joule per coulomb. Those are the units. Notice V is used for the parameter. It's also used for the unit. Energy is the parameter. Joule is the unit. Q is the parameter for charge. Coulomb is the unit. Okay. Amperage, on the other hand, or current, is charge per unit time. Charge per unit time. In units, that would be amperes is equal to coulombs per second. Amperes and coulombs are named after people, seconds are not. So what happens if we multiply voltage times current? What you get there is energy per unit charge times charge per unit time, and what you get there is energy per unit time. Does anyone remember what the time rate of change of energy is? Watts. What? Watts. Right, okay. The rate of using energy. Remember my working on the backyard, whatever you call those big things are. It's not a ditch witch, but yeah. So done the other way with the units, voltage times current, or amps, volts times amp. Volts are joules per coulomb. Amps are coulombs per second. Coulombs cancel out, and these are joules per second, which is a watt. Energy per unit time is power. So if you ever need to know what power is, it's voltage times current. That's power, and it's measured in watts. Okay. We don't have to do that section, but I thought I'd tell you about it. Now, there is a nice little thing, new technology on Tesla's high-performance electric automobile that's in the news a lot these days. You can read that if you'd like. The glossary is there on page 496. We didn't do all those words, but the ones that we did cover would be pretty good to know. The formulas you might need to know: 17.3, this is on page 497. We did a little with 17.4, but don't sweat that too much. We did a little with 17.5, so don't sweat that too much. But we did do 17.6, 17.7, 17.8, and that's pretty much most of those formulas you need. Review questions, you can review any of those who pertain to the sections we did. Review problems, basically only the ones that relate to what we covered in class. I won't go through and try to figure those out, but I'll give you a hint. When you see these circuit diagrams, like the ones we were just doing, those would be good ones to do. Okay? Now, when you see batteries in series or parallel, don't worry about those. When you see resistors in series or parallel, those are the ones to pay attention to. All right. Now we're moving to magnetism. Now, this is chapter 17. We're going to do, chapter 18. Oh, wait, before we do that, I'll come back to that. Unfortunately, Gracie left before I caught her, before I realized that here's the test for chapter 17. All right. A few of you still have it turned. One has it turned in test 2. A few of you have it turned in test 3. Quite a few have it turned in test 4. So here, I think, is test 5. Good deal. Thank you. Okay. Good deal. Thank you. Good deal. Thank you. My goodness. More the merrier. Okay. Good deal. Give me something to grade this weekend. All right. Is this which one?
That's the second.
Okay.
Yes, second.
That's what?
Yeah.
That's the second one. Yeah. Okay. All right. I hope people aren't leaving yet. I haven't given you.
I'm going to the restroom.
Okay. This test. All right. I don't think this has any corrections on it, but if you do have any questions, please ask, because this is a terrible test bank. And if you would see what I have to go through to grade them, because most of the answers are wrong. I have to go and work out every problem just about to figure out the correct key. Because the key that they send is usually maybe close to halfway right, but I don't know which half. Okay. So, as I was starting to say before, in chapter 18, I keep saying 17. Chapter 18 is magnetism, and we're going to cover sections 18.1, 18.2, and then we're going to jump down to 18.7. Okay? Then we're going to go to chapter 19, and in that one we're going to do 19.3. If we have time, we may do 19.4, but we're going to try to do 19.5. So the only ones we have to do are 19.3 and 19.5, but if we have time, we'll try to do 19.4 because it sort of ties what we've just done with what we're doing in chapter 19. So what we've got to do, as much as we can, 18.1, 18.2, 18.7, 19.3, and 19.5. Just 5 more sections, and if we have time, we'll do 19.4, and we may do a couple others just to tie it all together. All right, so let's start with chapter 18. So what I've got to do is get out of this and out of that, and where is chapter 18? All right, here we go. Let's start with first slide here from current slide. All right. Magnetism. Now, I don't know if you remember when we started the electricity chapter, we said that people understood just little bits and pieces about electricity, not very much at all, not why on any of it. It was mostly a parlor game, okay? People would rub amber with wool or something like that and go around and shock their friends, and people would jump. That was static electricity. No one understood why, but that was what was happening. Magnetism, on the other hand, probably people have understood little bits about it way longer. What is one thing that people have used magnetism for forever? Say again? You may have been right.
No.
Have you ever driven a ship? Probably not. But where would you use magnetism there? If you're out in the middle of the open sea, I'll tell you, the horizon never changes. Everything looks the same. You can't tell if you're going what direction. So what do we use? A compass. And how does a compass work? It's a magnetic needle sitting in a pool, and it always points pretty close to due north. Okay? That's magnetism. Okay? In this chapter, chapter 18, we'll talk about magnets, characteristics of magnets, and some of the features you might say, of magnets. So let's see what the first slide is. Well, that's on down the road a little ways. Let me do a little bit more first. Now, just give you there are only 3 naturally occurring magnetic elements. Only 3. Anyone happen to know what they are? Iron, nickel, and cobalt. Iron and nickel are pretty prevalent. Iron especially prevalent. Nickel less so, but cobalt fairly rare. Those are the only 3 naturally occurring magnetic materials. Aluminum, copper, silver, gold, all these things that conduct electricity pretty well, nothing for magnetism. Only iron, nickel, and cobalt. Okay? Don't know if that's coming back or not. This system is just doing crazy tonight.
Something about a magnet. I was thinking about when my dad had these big magnets.
Right.
And when I was little, I used to try to put them together.
Right.
Of course, they wouldn't go together. It was just.
Yeah. Do you know why? Okay, magnets are always, that leads me right into it. So let me first give you this definition, then we're going to hit on that. Metals with the ability to track pieces of iron or steel are said to be magnetic. Okay? Metals, and generally it's only metals that are magnetic that have the ability to attract magnetic materials, well, pieces of iron or steel, let's put it that way. Are said to be magnetic. Okay, now, steel, anyone know what steel is? It's a form of iron. It's an alloy of iron. So it's mostly iron. It's just harder, stronger than iron because you mix a few other metals with it and it gives it more strength. Stainless steel is iron that won't rust. It has chromium in it. Now, the more chromium you have, the less likely it is to be magnetic because you're bleeding out the iron and putting more chromium. But that's what we mean to be magnetic. Now, one deal about magnets. Now, this is, if you remember, when we're doing electricity, what was true about electricity? You had 2 different kinds of charges. You had positive charges and you had negative charges. Okay? What was true about positive charges? They repel each other. What's true about negative charges? They repel each other too. But what's true about a positive and a negative charge? They attract. Now, getting at what you were just talking about. Magnets are somewhat similar, but not quite the same. Magnets are always pieces of metal, okay? Iron, nickel, or cobalt, or some alloy of them, okay? Now, one end of that magnet is always what we call a north pole. The other end we call a south pole. The reason for that is first magnets were used for navigation. One pointed north, one pointed south. That's why we call them north and south poles. So whereas charges are always 2 charges, either positive or negative, so are magnets are always dipoles. One end is going to be positive, one's going to be negative. Okay. So much so, okay, I think I'll show the next picture here. All right. Now, this is getting at what you were doing. But what I want to point out to you, what we have here are two magnets. Here's the North Pole, here's the South Pole. Notice that all the iron filings, what you've done is sprinkle iron filings here, which are magnetic materials, and they all are attracted to the poles. But notice they're not attracted to the middle of the bar. Now, if they showed the other end of the bar over here, the South Pole for that one, guess what? Iron filings all around it, but none in the middle. If they show, let's just pretend that this is the end of that one. Shift it up a little bit, and you see the iron filings are attracted here. Now, what has caused these to come here is they were trying to get away from that North Pole, because North Poles repel, or like poles repel, unlike poles attract. So that's what you were describing. If your dad had those two magnets, you were trying to push a north to a north, and you couldn't do it. Arnold Schwarzenegger couldn't do it. You know, the strongest man on the earth couldn't do it, because you cannot force North Poles to go to North Poles, or South Poles to go to South Poles. But if you get a north near a south, just like opposite charges, okay? Opposite poles repel, opposite poles attract, like poles repel. That's what this is illustrating. Okay. Now, let's imagine we have a bar magnet. That's what these are, bar magnets. So if I put this bar magnet down, let's say it's about like this pen. Oh, let's use this. Let's assume that's a bar magnet. I put it down and sprinkle iron filings. All the iron filings are going to go near the two poles, North Pole and South Pole, right? So, what if I want to isolate one of those poles? And by the way, no iron filings go in the middle, much at all, okay? So what if I say, well, what I'm going to do is take this magnet and break it in two, or saw it in two, or anything, get it into two pieces. Now I've got a North Pole, now I've got a South Pole. Look at me, I've got monopoles. No, I don't. Guess what? That middle of the magnet, where you broke it or sawed it in two, if this was your north, that becomes a south, this becomes a north, that becomes a south. You can break a magnet as many times as you want to, and when you get to the very smallest piece, one's going to be a north and one's going to be a south. In between, they won't attract anything. But even though this didn't attract anything before, now it attracts all those iron filings. You cannot create a magnetic monopole. Now that's the difference between magnetism and electricity. You can have an isolated positive charge. You can have an isolated negative charge. You cannot have an isolated North Pole. Because for every North Pole, you're going to have a South Pole. For every South Pole, you're going to have a North Pole. Never can you isolate what they call a magnetic monopole. Okay. So, here are the two statements that they have in the blue box in the middle of page 503. Unlike poles, okay, this is just showing the things. To phrase it the way they do here, unlike poles attract each other, and like poles repel. This is just showing the pictures of what happens. And here's something I'm going to get at now, because it's the next thing we're going to talk about, and it's why they're talking about it there. Notice how these iron filings tend to line up together. Okay? What I'm getting at is they create what they call lines of force. Notice how these lines are bending similar ways. These are coming together. What you may not see from where you're sitting, you got tons of these lines of forces between these two because they're really attractive. You have spread apart here because they're repelling. Okay? So, That's describing a magnetic field. Okay? So I'm going to erase what I've got here. Okay? And let me write this in. A magnetic field. Now, if you remember, we talked about electric fields too. A magnetic field, a force, near a magnetic pole I can't write, or near an electric current can be detected using another magnet. That's a pretty wordy sentence. Okay. Now, that's not a lot different from what we did with electric fields. If you remember, we said electric field, if you had some electric charge here and brought in a test charge, then you could tell what the field, which direction it was going. Usually your test charges were positive. If that test charge started heading this way, you know this is a negative, because test charge is usually positive. If it started pushing that way, you know this is a positive charge. The field lines always point away from positive charges toward negative charges. Okay? Well, in magnetic fields, they point away from the North Pole toward the South Pole. So the magnetic field lines are a lot like electric field lines. It's just that you can actually see them if you use iron filings, or at least see something pretty close to representing them, because the filings line up with the field lines. And that's why they put this figure in here. Okay. Now, they have a little bit better one in the book, and I wish I could draw it, but my drawings, you wouldn't be able to tell what I was trying to indicate. So I'll try to just show them to you here. If you got your books, you can see them. This is the top of page 504. Okay? This is actually a magnet, and they put iron filings around it, and you can see basically where the field lines are. They're all concentrated near the poles. There's a few in between, but not many. Concentrated near the poles, and they seem to follow curves or lines. Okay? If you place a little compass, which is a magnet, which usually points north, if you put those near those field lines, you'll see the arrow, the needle actually curves with the field line. It doesn't point north anymore. It points to actually the south, okay? Because unlike poles attract each other. So it will point to the south pole of that magnet. And so this is a really good illustration of that. Now, what the drawing does that the filings can't do is give direction. And it's what I said before. The convention is the magnetic fields always point away from the North Pole toward the South Pole. Always. Just like they point away from a positive charge toward a negative charge, the electric field lines. Okay. Now, everything they've shown so far is looking to be two-dimensional, but you realize a magnet is three-dimensional. If you have a bar magnet here, its field lines, if the north is this way and south is this way, its field lines are going in every direction away from the north and coming back together to the south. So it's a three-dimensional setup. Now, why compasses work is because the Earth is a magnet, a big magnet. Now, I don't know if any of you know much about say, geology and plate tectonics and that kind of stuff. But does anyone know what the predominant element in all the earth is? The most common element throughout all the earth? No, that's a compound, and that's on the surface of the earth. The predominant element throughout the entire earth is iron. Yes. Now, what we have when we're like in Birmingham and Bessemer, Pittsburgh, and those places, that's places where the little bit of iron made its way to the surface. If you go deep into the earth, really deep in the earth, you're going to hit mostly iron. Another element that's down there in large quantities is nickel, two of our naturally occurring magnetic materials. Okay? Now, the other thing about the earth is made up of a crust. The crust is really thin, just a few miles thick. Now that sounds pretty thick to me. That's nothing. Just a thin little crust. We live in the crust. We mine in the crust. We do everything in the crust. Very seldom do we get anything below the crust. But below the crust, they have a really thick layer, the earth does, called a mantle. The mantle is made up mostly of iron-containing minerals, okay? Mostly iron-containing minerals. You have a variety of them. We won't get into all that now. But inside the mantle, we get to what we call the core. Now, the core actually has two parts, but the outer part of the core is so much pressure, so much gravitational pressure. What happens when you push your hands together and rub them? They get hot, okay? Warm, yes, right. Why? Because pressure and motion produces heat. Well, that mostly iron minerals that are part of the mantle, as you get deeper and deeper in the earth, the pressure, all that weight on outside, pushing down, forcing those together, they get so hot, they melt. So most of the outer core of the earth is liquid.
Probably doesn't have anything to do with what you're talking about, but you said when you rub your hands together, they get warm. That made me think of when you have socks on and you're on the carpet and you rub your feet, and as soon as you touch somebody, they get like shocked or something.
Okay. Now that's because of static electricity, which we did in the last chapter.
That made me think of that.
Yeah, that's exactly right. Especially if the carpet has probably got some polyester in it, but the socks may have wool in it. So two different materials doing like this, you're rubbing off electrons off one onto the other, and then when you touch somebody, yeah, you shock them. Same thing happens with rubber-soled shoes on polyester carpet. Sometime when I did research at Southern Research Institute, we stayed, when we worked out of town, usually some of the cheaper motels we could find, because we didn't want to spend our money, on fancy digs when all we were doing is sleeping there. And they would usually have polyester carpet, and you'd reach in to touch the doorknob, and you'd get shocked, because rubber shoes on polyester probably are going to create a difference in charge. So it's something similar to that, what we have here. So we have, and the other thing about the earth, it spins, spinning pretty quickly, right? And since it's spinning, the iron part, the mantle, which is inside the crust, and the solid part, it's spinning. The liquid part just sort of sits there. It flows a little bit, but when they rub against each other, they knock charges off and get charges moving in circles. Those charges, and iron, it's mostly iron, create a magnetic field. The earth becomes a pretty big magnet. Not a super strong magnet, but definitely a magnet. Now, remember what I said? Your magnetic compass mostly points generally toward the north. There's a reason for that. The spin axis of the earth, that's true north. That's the actual axis of the earth, everything spinning around it. For some reason, because of the nature of the core and the irregularities in it and stuff, the magnetic north is not quite aligned with it. Here is the North Geographic Pole, the spin axis right there, North Pole. Over here in northern Canada, not many degrees off, but a few degrees off, that's where the magnetic North Pole is. It's still way up there, but not exactly. So if you're over here looking at a magnetic compass, it's pointing this way, whereas true north is that way. If you're here in Alabama, your magnetic compass is pointing this way, where true north is not far away, because they're almost lined up. So we're in a pretty good place for your magnetic compasses to work. Okay. Now, the Earth's magnetic axis is offset a little bit from the true axis of rotation. And it's not entirely clear why that's true. It just is. Okay? So, they have on here a magnetic equator. That's really not important. Very important. It's just where the field lines are weakest, where they're strongest is along that way. The field lines are sort of parallel to the Earth's surface here, perpendicular to the Earth's surface there, which leads to another issue that we'll talk about later. Now, there's a new technologies section at the bottom of page 505, and that's NASA's Magnetospheric Multiscale Mission, MMS. Where the S comes from, I'm not sure. Okay, you can certainly read about that. It's pretty interesting stuff. Oh, okay, I still don't see where it comes from. So anyway, that's the end of 18.1. No questions, no problems to do at 18.1. Now, if you remember what I said, we do 18.1 and 18.2. Now, this is where it basically is very similar to the Earth, and it's something I want you to remember. Here's a man's name, Hans Christian Ørsted, a physicist born in Denmark. He was the first person to discover the connection between electricity and magnetism. For centuries, millennia, people knew a little bit about electricity, a little bit more about magnetism, didn't have a clue that they were anywhere closely related. But Hans Christian Ørsted found out that they were. And here's basically what he discovered. So, you get a compass, okay? This compass is most of the time going to point to the north, okay? But if you put a direct current, that means through a battery, through it and put it near the compass, that will deflect it from pointing true north to pointing in a different direction. Okay? And depends on where this is. Now this is a pretty confusing slide, so I'm going to try to take it to you one at a time. Okay. Here the switch is open. There is no current going through the current. Okay? Your compass is here, and it happens to be pointing to true north. That way. Or magnetic north. That way. All right? Now, if you have the positive set up here and going back to negative here, if you close the switch, now the current flows from positive to negative. And when the current flows that direction, okay, here's what you use. The right-hand rule. The right-hand rule says if you point your right thumb in the direction of the current flow, so I'm going to do that way, your magnetic field goes around it like this. So now you've got a magnetic field going that way. So north is pointing this way, south is pointing that way. So your compass deviates from true north and points this way. not to north anymore. North is this way, it's pointing there. Okay? Now, if you reverse the current and bring it in this direction, now your current's flowing this way, your magnet's doing this, north is pointing this way. Now this is with the compass underneath the wire. If you put the compass on top of the wire, again, with the switch open, it just points north. But if you close the switch, okay, if you close the switch, now it's pointing, get my fingers like this, it's pointing this way. So north is over the wire, it is under the wire like this, okay? So north is pointing in that direction. When you do it, the compass on top of the wire, then the north is pointing in this direction. Switch the wire, so it's flowing in this direction. Now the current is flowing here. Here when it was under the wire, the north is this way. On top of the wire, north is that way, okay? So your compass changes depending on the current. Oersted was the one who found this out, that a moving charge induces a magnetic field. It's an important thing to remember. A moving charge induces a magnetic field. And that's why the spinning earth with flows of charge in the earth creates a magnetic field and the earth becomes a magnet. Anytime you have a moving charge, you induce a magnetic field. Now, if I were to put a compass near this wire, now it's got a lot of insulation, so it's not going to do anything. But even if it was bare wire here, I wouldn't be holding it, okay? But if it was bare wire here, it still wouldn't deflect your compass. Why? Because this is alternating current. It's just going back and forth, back and forth, back and forth. The needle wouldn't have a chance to adjust. But if you did this part, which when it goes through, here it is, the converter from AC to DC, if I had that bare wire, then it would deflect the compass needle, because a moving charge in one direction is going to create a magnetic field. What happens when you switch the poles of the battery, then you change the direction of the current, so it flips the field around. So that's why that figure is true, and this is what Hans Christian Oersted discovered. Now, how strong is this magnetic field? Generally not very strong, okay? And the strength of this field is given by, we're going to get to that in just a minute. Let me write on this one, okay? The direction of the field near a current in a straight wire is given by Ampere's rule. And here's Ampere's rule, and this is going to demonstrate it for us. Hold a wire, this sounds stupid, but hold a wire in your right hand. And by the way, this is called the right hand rule. Okay? With your thumb extended, thumb extended in the direction of the current. Now, what current we're talking about? The conventional current, going from positive to negative, okay? In the direction of the current. Then your fingers of your right hand circle the wire in the direction of the flux lines. Then your fingers, again of your right hand, circle the wire in the direction of the field lines. And this is what this figure is illustrating. Okay? If your current, conventional current, going from plus to minus, is in that direction, point your right hand in the direction of the field of the current, your fingers will go in the direction of the field lines. So a compass over here would point this way, compass over there point that way. Compass here points that way, compass here points that way. Points in the direction of the field lines. Okay? Why they have these two, I don't know. Just as illustrating the same thing as this. I don't see why I have two of them, but it does. Oh, I see. They don't have your thumb here. Okay. The current is in the direction there, just like your fingers would be pointing if you held it in your hand. Oh, what's sort of dumb about it? Well, number one, that's the longest thumb I've ever seen. No, but that's beside the point. If that was a current carrying wire, you aren't going to hold it in your hand because you're going to get shocked, okay? But if you point your thumb in the direction of that, then that's the part to me that was sort of dumb. All right. Now that's the direction of the current. How about the magnitude of the current? Okay? The magnetic field near a long current carrying wire is measured in, guess what units? Tesla, okay? Just like the car company, okay? Named after Nikola Tesla. Okay, he has A at the end of both names. He, by the way, worked for a few years under Thomas Edison. Both brilliant, brilliant people. But Edison was sold on the fact he thought direct current was the way to go, and he feared alternating current was dangerous. Okay? Tesla said, no, alternating current is the way to go. Direct current's not going to give you strength enough to go long distances. One of the few places that Thomas Edison was wrong. Tesla was right. Thomas Edison's pretty famous. Tesla, not so. He worked with another famous guy at the time named Westinghouse. We know his name. Appliance company is named after him. But anyway, here is the strength of the magnetic field measured in Tesla. The symbol for magnetic field is capital B. Now this ought to be a vector. I'm going to draw it as if it is, but what we're talking about here is the magnitude. So I'll take the arrow off of it because we're just talking about its magnitude. And here's what it is. Here's a strange little symbol, mu naught. We'll talk about that in a minute. Times the current. You have to have current to produce a magnetic field. Moving charge produces magnetic field. Divided by 2 pi times capital R. What is capital R? It's the perpendicular distance from the center of the wire. So this would be capital R, that would be capital R, that would be capital R, depending on where you are, how far away you are. So it falls off, it's stronger the closer you are to the wire, weaker the further you get away. Okay? So this is the perpendicular, I'm going to use that symbol for perpendicular distance from the center of the wire. It's not resistance. Don't get it confused with that. We don't talk about magnetic resistance. We only talk about electrical resistance. The distance, perpendicular distance from the center of the wire. Now, what's that other? Okay, y'all know what pi is, right? It's just a number, 3.1415, blah, 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 blah. Okay. Now, what is mu naught? Mu naught is a dimension quantity. And this is a strange sort of thing. It's 4 pi times 10 to the minus 7th Tesla meters per amp. Okay? Tesla, because you got to have Teslas out here, meters, because you got to cancel the meters from here, amps down here, so it will cancel the amperage from there. So you have a 4 pi up here, a 2 pi down here, so it basically wind up being equivalent to 2 times 10 to the minus 7. But that's neither here nor there. Now, what we've just been describing, the magnetic field may also be described in terms of magnetic flux density. Now here again, they're giving us a name that I don't think they've done a good job of defining, flux density. I'm trying to see if I missed it somewhere. They talked about it before, and here they're talking about it again, and I don't think they really have defined it well for us, okay? But magnetic flux density is another name for the magnetic field. So this is measured in Tesla, capital T, and this is magnetic flux density. I can't write. Magnetic flux density. That's what Tesla measures when you're measuring your magnetic field. Okay? Now, magnetic flux is given the symbol phi. That's magnetic flux. You don't really need to know this, but I'm just giving it to you so maybe some of this will make more sense. Per unit area. That's what flux density is, the magnetic flux per unit area. Now, they haven't told us what magnetic flux is, and I don't think they really will. Now, before they decided to name the SI unit for magnetic flux density, this is the SI unit. Before they used the SI unit, they used an earlier unit named the Gauss, named after, I think his name was Johann Gauss, okay? Very famous mathematician and physicist. Did lots of work in many areas. And one Gauss, okay, and by the way, it's named after someone, so it's capital letter. The unit for a Tesla is 1 watt per meter squared, okay, per square meter, okay. Now they put a weird symbol in there. And I can't even tell what in the world they're trying to say there. The unit of Gauss, 1 Gauss, G-A-U-S-S, is 1 mx, and they don't say you what the mx stands for, per centimeter squared. Okay. That's rather bizarre. Okay. Now, let's go back to our other slide. Goodness, I hope I can make it till the end. Goodness, I'm going downhill fast. All right. So let's go from current slide. Get our pen back. Okay. A power line carrying 400 amps. What is 400 amps measure? What unit are you measuring with 400 amps? Oh, we're just doing it in the last chapter. That's your current. Current is measured in amperes. 400 amps of current is 9 meters above a transit used by a surveying student. We don't really know or care what that is, but 9 meters, if here is your power line up here, and here's your surveying student down here using his transit, okay, whatever that is, there's 9 meters between that. 9.0, how many? 0.00 meters. Okay? That is the R. That's the distance between the current and the device that may be affected by the current. Okay? That's all they tell you. It says find the magnetic field. What's the symbol for magnetic field? Ooh, how long ago? If you're on page 507, just look up the page. Magnetic field is B. Magnetic field, for some reason they use B. B is equal to mu naught times I divided by 2 pi. I started to say 4 pi. 2 pi times R. Okay? But remember the mu naught is 4 pi times 10 to the minus 7th. And that would be Tesla meter per amp times 400 amps. Okay? So the amps cancel out. Divided by 2 pi. Well, the pi's cancel out and 2 will go into 4 twice. Times the radius. The radius is 9.00 meters. So what's the magnetic field felt by the student down here with his transit, I think is what he called it? Yeah. What would that be? Well, 2 times 400 would be 800 times 10 to the minus 7th. The amperes went out. The meters go out. So that gives you Tesla divided by 9.00. And that unit was meter, but we already canceled it out. So if you do 800 EE or EXP 7, negative 7, however your computer does that, calculator does it, and divide it by 9 and see what you get. $800 EE or EXP negative 7, whether you do 7 plus minus or in parentheses 7, in parentheses minus sign 7, divided by 9. Anyone get it? Not going to be very much. Something. Anyone do it yet?
I would have, but my phone died.
Oh, I see. Anyone got it? 800 EEEXP, either negative 7 or 7 plus minus, however you do it on yours, divided by 9. Anyone got it? A little louder. Okay. In scientific notation, it would be 8.89 times 10 to the minus 6. Because you see, you can wipe out one of these and make it minus 6, and 9 will go into 80 almost 9 times. 8.89 times 10 to the minus 6 Tesla. That's how much magnetic field he feels down there. Okay. The magnetic field from the power line would be that. Now it says with the current from south to north, Ampere's rule shows that the direction would be from east to west. Because you see B is a vector quantity, so in addition to the magnitude, you really ought to give the direction. Now what's sort of crazy about this problem is this. If you have a power line, you're not going to be running 400 amps. You're just going to lose way too much. And most power lines are AC, so you wouldn't feel it at all, okay, or not much anyway. So this was sort of a made-up problem, okay. Now, the angle of the resulting vector, the Earth's magnetic field plus the wire's field, makes with the field of the Earth, that's the B sub E, the B of the wire. We really haven't done that. Y'all haven't had trig, have you? Okay, so we're going to leave off those. Now, the original problem said if the Earth's horizontal component of magnetic field is 5.20 times 10 to the minus 5 Tesla, so you see the Earth's magnetic field, B sub E, was 5.20 times 10 to the minus 5 Tesla. You see, that's much stronger than the magnetic field from a wire 9 meters high. 9 meters is a long way. This building, this room is no more than 3 meters tall, so it'd be a 3-story building. This story, the next one, and one more on top, which isn't there. It's pretty high up there. So that wouldn't, it would have a little bit of influence, but not a lot. Okay? He said, what error would be introduced in the angular measurement? That's the B part. And since you haven't had probably enough trig to do this, they give you in the book, it'd be about 9.7 degrees. Not that great. So don't worry about the trig part. Now, I think we've just about run out of time, right? So where we'll pick up next time is on the magnetic field of a loop. And we'll have another new formula there, and we'll do a little bit of working with that. Any questions? Thanks for hanging with me this long. Sorry about the throat.